So today I'm going to introduce you to derivatives. You already have seen the reason for derivatives when you were trying to pinpoint an IROC and you couldn't because you can't divide by zero. So to find an instantaneous rate of change or the slope of a tangent line at any given point, that's where a derivative swoops in and allows you to not have to use the AROC to estimate or approximate what the IROC is. Okay, the foundation, the part we're going to do today is very important. So I'm going to go slow and easy. Okay, the best way to understand the definition of a derivative is to start by looking at the slope of a linear line. And you guys know that the slope is the change in the y's over the change in the x's. Okay, now think about the graph of that line. The slope measures the steepness of the line. Okay, so the change in the y's over the change in the x, and that finds the slope from this point to this point. So to change some notation, instead of this being x sub 1 and x sub 2, I'm going to let this be x sub 1. And then instead of x sub 2, I'm going to let this be x sub 1 plus h. So guys, h represents the distance that you're traveling here. So if this is at 3 and I'm going 2, then this would be a 5. Okay, so it's this one plus the distance. So h is the distance that you're traveling. Okay, so then the y values, so this y value for this point is going to be f of this x value. And this y value is going to be f of this x value. Okay, so we've got x and x plus h over f of x minus f of x plus h. So the x minus x over y minus y. Okay, well that's all easy when we're talking about linear functions. But what about the slope of a curved function? So our slope formula no longer works because we aren't a straight line. But if we can find the approximate slope, if we took the slope of the line between 2 points. This is called the secant line, and we did this the very first day. So we took these 2 points, and we found the slope, and that was the average rate of change, y minus y over x minus x. Okay, but if I take that y minus y over x minus x, remember he's y, and he's a y, and he's an x, and he's an x. So y minus y, that's him minus him, over x, well, let's do it the other way. X, hold on, sorry. There we go. This x value minus this x value. Okay, so if I do that, if I do x sub 1 plus h minus x sub 1, then the x's are going to cancel, and it's just going to leave me with h. So this is y minus y over x minus x. Okay, so we've done no calculus yet. We've just sort of renamed some things and replaced some things. Okay, now as you can see, the farther apart the 2 points are, the less the slope of the secant line corresponds to the slope of the curve. As the points get closer and closer, the more accurate the approximation is. Okay, so automatically you should start having limit flashes in your head. So what this is saying is if my two x values are really, really far apart, This line, the secant line, does not give a great representation of the slope of the curve. But as this distance, remember that distance is h, if that distance gets smaller and smaller and smaller, then these 2 points get closer and closer, then this secant line becomes a better approximation of the slope of the tangent line. So if I want that h to get smaller and smaller and smaller, then we're going to use the definition of a limit. Okay, so in fact, there is one line called the tangent line that touches the curve at exactly 1 point. The slope of the tangent line is equal to the slope of the curve at exactly this point. Ooh, that's a good sentence. Let's do that one more time. The slope of the tangent line is equal to the slope of the curve at exactly this point. Okay, so if I were to have, let's do another shape. If I were to have a function that does this, okay, and I want the slope, now the slope of this line, the slope of this curve changes. I mean, it's positive and steep, and then it flattens out, and then it's negative, and then it flattens out, and then it's positive again. So the linear slope of this line is constantly changing. So the slope of this curve is going to be different at every single point. So well, I'm going to pick this guy right here. Well, the tangent line, oh, that was really bad. Let me try that again. Okay. The tangent line, the goal is to only touch once at that 1 point. Oh, that's much better. Okay. So the slope of the tangent line is the slope of this curve at that particular point. But if I pick a different point, I have to draw a different tangent line, and it's going to have a different slope, and which makes sense because that function has a different slope at that place, at that value. Think about this point. Here's your tangent line. Its slope is 0. So the slope of the curve at that point is 0. So you guys see how this tangent line changes as it slides around this curve. So the slope of that tangent line is going to change. All right, so I'm going to read that sentence that I underlined one more time. The slope of the tangent line is equal to the slope of the curve at that exact point. But when I change points, I got to change tangent lines, which means my slope is going to change. So an infinite number of tangent lines along a curve. So to get super accurate for a particular point, what I want to do is shrink h down, which is the distance between the 2 points that I'm using to estimate, down to an infinitesimally small amount. How do we do that? With limits. I want to take the limit of y minus y over x minus x. Remember, that's what that simplified to. But I want the limit as h, that distance between those 2 points gets infinitesimally small. So I want it as the limit goes to 0. So guys, this right here is the definition of a derivative. It is the cornerstone foundational block of half of calculus, really of all of calculus. Okay, this is the definition of the derivative, and we call it, this is called f prime of x. F prime of x. You can also see it written these ways, except this is a typo. That should not be a C. That should be an H. So they can replace X's with C's. You can also see it with this delta X. Delta in math means change. And h is the change in x. Remember, it was the distance from one x to the other x. So h is delta x. So those are just other ways that you can see it. Okay. In addition to f prime of x, which is red, f prime of x, other notations are used to denote the derivative of y equals f of x. The most common are f prime of x, dy dx, y prime. Um, this one is not so much used, and this one I hardly ever see. But this one is d f of x over dx. And we'll get much more into the notation later, so I don't want you to stress. I really want you to focus on these three for now. So f prime of x, dy dx, and y prime. The notation dy dx is read as the derivative of y with respect to x, or simply dy dx. Using limit notation, you can write dy dx, y prime, f prime of x. Those are all your derivative notations. Is the limit of the change in y over the change in x as the change of x goes to 0. But the big fancy one is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Guys, remember, delta x is the same thing as h. H is that change in the y value, in the x values. Finding the derivative is called differentiation of a function. Derivatives equal differentiation. So if I say, I want you to differentiate that function, that means find its derivative. Okay? If I ask you if it's differentiable, then I want to know, can you find the derivative? Okay, so let's do some. It says, find the slope of the curve f of x equals x squared at the point 2, 4. Okay, so let's hold on just a second and let's make sure we have a visual representation of what we're doing. And this is y equals x squared. So when x is 1, 1 squared is 1. And when x is 2, we're going to be at 4. Negative 1 is going to be 1. 2 is going to, or negative 2 is going to be a positive 4. 3 would be 9, but I'm not going to go up that high. Okay, and it wants to know the slope of the tangent line at the point 2, 4. So the tangent line, and I'm terrible at drawing straight lines. Now pretend that touches. That's supposed to touch at that point. So guys, I already know that my slope should be positive because that blue line is going up, and it should be pretty big because that's a pretty steep line. Okay. So to do this, I'm going to use my limit definition. Okay, and I'm going to use h's instead of the delta x. So I have the limit as h approaches 0 of f of x plus h minus f of x over h. Again, that came from y minus y over x minus x. Okay? So the first thing I need to do is find f of x plus h. So I have to have good notation. Keep my limit until I pull the trigger on the limit. So f of x plus h means take an x plus h and plug it in. So I would have x plus h squared, which I'll lobster in a minute, minus f of x. So that's just plain old x squared. That is a shark, but there's nothing to run it through, so I'm not worried about that, over h. Okay, now I'm going to clean. Good notation, limit's still there. I'm going to take this in my brain and write it twice and lobster it out. So that's x squared plus 2xh plus h squared minus x squared over h. Okay, now I have the limit as h approaches 0. Clean up the top. Those guys cancel. And just my OCD, I'm going to put the h squared first just because it makes me happy. Okay, so I'm cleaned up and I'm to here. So I'm kind of ready to pull the trigger on my limit, but if I do that, I'm going to get 0 over 0. So, got to be a way to fix that. And if I look at this, I can see that I can take an h from everything. So I have the limit, h approaches 0, take an h from everybody. So h plus 2x, and that would be over 1. So I'm going to leave that alone. Now I can pull the trigger on my limit. So if I plug a 0 in for h, I get a 2x. Okay, ladies and gentlemen, you just found your first derivative. This 2x right here is your y prime, or your f prime of x, or your dy dx. So what you have just found, I'm going to use this one, is the derivative of him. Okay, now let me be crystal clear. This is the formula for the slope of the tangent line, not the secant line, of the tangent line at any given point. That f prime of x has nothing to do with the point 2, 4. All we based that on was the mother function y equals x squared. Okay? So now I can use that equation, which finds the slope of the tangent line at any given point. Oh, we're going to say that 1,000 times. The derivative is the slope of the tangent line at any given point. Well, I have that, but they're asking about a very, very specific point at 2, 4. Okay, so f prime of 2, because that's my x value, is going to equal 2 times 2, which is 4. So 4 is the slope of the tangent line at the point 2, 4. Now let's see if that makes sense with our drawing. Slope is 4. Well, we said it had to be positive and it had to be pretty steep. And that's exactly what 4 is. Okay. Number 2 says find the slope of the same curve at the point 5, 25. Well, guys, you've already found the formula. You already know that f prime of x equals 2x. I now want to find f prime of 5. We'll plug 5 in. You get a 10. So 10 is the slope of the curve y equals x squared at the point 525. Okay, I'm going to try another one. What about find me the slope of the same curve at the point, let's see, we did the point 2, 4. Let's do negative 2, 4. So again, f prime of x equals 2x. I'm going to plug in a negative 2, and that's going to give me a negative 4. So what this is saying is that negative 4 is the slope of the tangent line at the point negative 2, 4. Well, let's go look. Negative 2, 4 is here. I'm really bad at drawing straight lines. There's your tangent line. And does it make sense that it is the same as this one? Just opposite sides. It is the same steepness as its counterpart, its symmetrical counterpart at 2, 4, but its sign just happens to be negative because the slope of that line is going downhill. But again, same steepness. Okay, let's try this. find me the slope of the tangent line at 0, 0. Well, f prime of x equals 2x. I'm going to plug in the 0 for x, and I'm going to get a 0. Okay, so here's what this is saying. 0 is the slope of the tangent line at 0, 0. Well, you know that a 0 slope is a horizontal line. And that is the slope of the tangent line at 0, 0. If I found the slope at 1, 1, so if I plug in a 1, 2 times 1 is 2, I'm going to get a 2. So here we are, and the slope of the tangent line is a 2, which makes sense because it's positive, but it's not quite as steep as the 4. It's a 2. Guys, I can do this for every single point on this function using its derivative because, one more time, the derivative is the equation for the slope of the tangent line at any given point. The derivative is the slope of the tangent line at any given point. One more time. The derivative is the slope of the tangent line at any given point. All right, let's try it. Find the derivative, which is the slope of the tangent line at any given point, of f of x equals 3x squared at 448. Okay, so the first thing I need to do is find my derivative. So, definition of a derivative is the limit as h approaches 0. He needs to be burned into your brain. Okay, have good notation. Do not lose your limit until you pull the trigger on your limit. Okay, so f of x plus h means take an x plus h and plug it into f of x. So 3 times x plus h squared minus plain old f of x, so 3x squared. That is a shark. I would have to run it through, but there's nothing there. Okay, limit's still here. I'm going to lobster that. I'm going to distribute my 3. Feel free to pause this. Go at your own pace. And now I clean. Again, I'm going to put the x squared dude, the h squared dude in the front, just because I can't pull the trigger on my limit because everything would go to 0. So my limit is still there while I take an h from everybody. Pull the trigger on my limit, plug a 0 in for h. I get a 6x. Okay, so think about who that is. That is your derivative. He is f prime of x. If f of x is a 3x squared, f prime of x is a 6x. And again, the derivative is the slope of the tangent line at any given point. You give me a point, I can tell you what the slope of the tangent line is at that point. They have given me 448. So I want to find f prime of 4, which is 24. What that means is the slope of the tangent line at 448 is 24. Very steep, very positive, and very steep. But this is 3x squared, so you know that's a parabola with a vertical stretch, so it's getting steeper faster. Derivative is the slope of the tangent line at any given point. This is your derivative. This is you finding the derivative at a specific point. Okay. All right, changing functions. We're leaving quadratics and we're going back to linear. 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 Think about that for a second. Find the slope of the graph when c equals 2. C and x, same thing. I don't know why they do that. Limit as h approaches 0 of f of x plus h minus f of x over h. Again, burned into your brain. Limit h approaches 0. Okay, f of x plus h. That means take an x plus h and plug it in. So 2 times x plus h minus 3. Okay, minus f of x. Okay, guys, minus. Now watch, I'm putting that in parentheses because he is now multi-termed, and that shark has to run through it. So limit as x approaches 0 of 2x plus 2h minus 3 minus 2x plus 3 all over h. Now I'm cleaning. Oh, looky there. 2h over h, which is 2. So if I take the limit as h approaches 0 of 2, there are no h's. So I get a 2. So what we're saying is that f prime of x is 2. Okay, the derivative is the slope of the tangent line at any given point. Well, guys, this derivative is a constant. Like, there are no x's. So if I ask you to find me the slope where x is 2, or x is 5, or x is negative 100, there are no x's to plug that into in my derivative because the slope is always 2 because it's a linear function. The slope never changes. This curve, air quotes, it doesn't curve. It's a straight line. Its slope is always 2. So it makes perfect sense that when we took the derivative, we got a constant. And that constant is my slope, y equals mx plus b. I know the slope was supposed to be 2 before I ever started this problem. Okay, back to quadratic. This is a parabola that's normal, shifted up 1. Okay, so, and I've got 2 different points. So the first thing I need to do is find the derivative, which is the slope of the tangent line at any given point. So let's do that first. I'm writing my formula, which should be burned into your brain. Now I'm gonna plug some stuff in. F of x plus h means plug an x plus h in, and then minus plain old f of x, but I put them in parentheses because that is a shark. Okay. All right, tell you what, pause the video, go clean all this up, then hit play and see if you get it right. Okay, I got the derivative of f, or f prime, is 2x. And I'm going to write it up here. This one wants the slope at 0, 1, so I'm going to plug in the 0. So f prime at 0 would be 0. So the slope of the tangent line at the point 0, 1 is 0, which, stop and think, pull the graph standpoint in here. This is a parabola shifted up 1. So the slope at the point 0, 1 should be 0 because it's where it bottoms out. It's a horizontal line. Now I want f prime of negative 1. So 2 times negative 1, which would be a negative 2. So that is the slope of the tangent line at the point negative 1, 2. Okay, for the 50th time, this is the slope of the tangent line at any given point. This is the slope of the tangent line at this particular point. This is the slope of the tangent line at this particular point. Okay. All right, a little more interesting, a little square root action. So, definition of a limit, again, burned into your brain. Okay, I want you to hit pause. I want you to do just the setup and then hit play and see if you get it right. Just the setup part. Okay, so there's my setup. Now, if I pull the trigger on my limit, I'm going to have, if all my h's go to 0, bottom will be a 0, top will be 2 root x minus 2 root x. The top's going to be 0, so that's bad. But you know ways to compensate for that. So we're going to go conjugate using the top. Okay, now this is big, so I want you to pause, lobster all this mess out, clean it up, then hit play and see how you did. Root of cow times root of cow is a cow. Root of cow times a cow is a cow. Again, I'm moving fast because I assume you've already done this. You're just checking your work. Okay, I have cleaned. I can now pull the trigger on my limit. So, and make sure you have good notation. Make sure your limit carried all the way through all that crap. So now if I let h go to 0, I have 4 over 2 root x plus 2 root x, which is 4 over 4 root x, which is 1 over root x. So f prime of x equals 1 over root x. Incidentally, which also could be written as x to the negative 1/2, just to remind you of that, because that's going to come into play next class. Okay, it said find the derivative of the following function at any given point. Well, I found the derivative, which is the slope of the function at any given point. It didn't give me a particular point to plug in. I was just supposed to find the derivative. So there he is. Okay, this one's got a little bit more meat on it. We're going to find the derivative. Okay, so here's my challenge to you. Pause it. Go as far as you can until you get stuck. Hit play. Let me catch up to wherever you are and help get you unstuck. Then pause it again. Try to do as much of this problem as you can without me. Use me as your backup. Okay? All right, I can't cube that in my head. I can square it. So there's one of them, and then it's squared is that. So now I have to do this. Okay, so that's it cubed. And the shark. We talked about how the number crunchy stuff was coming back. There it is. There's no calculus in any of that. That's math 2, a little bit of math 1. So just be careful. Take your time. Watch your powers. Watch your details. I think that's it. Okay. Taking an H from everybody. Oh, nope. Now I'm pulling the trigger on my limits. I dropped the limit part. 3x squared, he goes, plus 2. So f prime of x equals 3x squared plus 2. Direction said find the derivative. There she be. Now notice this. Started with a cubic function and my derivative is quadratic. If you go back and look, when I gave you quadratic, your derivative was linear. When I gave you linear, your derivative was constant. So the derivative will knock it down a degree. It'll knock a polynomial down a degree. Okay. Find the derivative of f of t or f of x, same thing, equals 7. Okay, think. 7. What does that graph look like? What does y equals 7 look like? There is the equation y equals 7. I'm asking you to find the derivative, which is the equation for the slope of the tangent line at any given point. The equation of the slope of the tangent line at any given point. So I want you to think about the tangent line of y equals 7. Tangent line's never going to change. So the slope of all these tangent lines that are going to touch y equals 7 are all going to be horizontal lines, so their slopes are all going to be 0. No math needed. I mean, you can do the formula, but there's no point. If you recognize what a derivative is, then you can do that with no work whatsoever. The derivative of a constant is always 0. The derivative of a constant because the horizontal line is always 0. Okay. All right, here I go. Okay. Plug it in. And again, pause me. Go plug it in. See what you can do. Then unpause me to help get you unstuck. That's the best way to do this. Okay, cut the cord. Do this on as much as you can on your own. Little bojangles. Pull the trigger on your limit. There we go. Which, by the way, is the same thing as that. Just, again, a nice refresher. Okay, so definition of a derivative. And again, this is just y minus y over x minus x as the limit as h approaches 0. Remember, we use that new notation. So it was f of x plus h minus f of x. Those are your two y's. And your two x's were the x plus h and the x. If you clean that up, the x's cancel, so I'm left with an h. Remember what h represents. H represents the distance between those two x's, that horizontal distance. So what I want is I want that h to go to 0. I know I can't divide by 0, but I want it to get as close to 0 as humanly possible. So that's my definition of a limit. When you find this limit, you have found the derivative. The derivative is the equation for the slope of the tangent line at any given point. Then you can plug in any x value into that derivative, and that will give you the slope of that curve at a particular point. The process of finding a derivative of a function is called differentiation. A function is differentiable at x if its derivative exists at x and it's differentiable on an open interval a to b, if it's differentiable at every point on the interval. Okay. Derivatives are not defined at a given point. Okay, derivatives. So you can't always find a derivative. Derivatives are not defined if we are discontinuous at the point in which you are finding a tangent line. Here's a great example. I can find the derivative of him wherever he exists, but I cannot find it at, I cannot find it at 0 because I'm not continuous at 0. I'm not continuous at 0 because the limit as x approaches 0 of this function does not exist, because it does not exist from the left. One more time. I'm not continuous at x equals 0 for this function because the limit doesn't exist from both sides. Okay, so I can find the derivative of y equals x squared. I just can't evaluate that derivative at 0 or anything negative because it doesn't exist over there. You cannot find the derivative if the tangent line would be a vertical line. So if I gave you some sort of ellipse, you could find the derivative of it, but you couldn't evaluate that derivative here because its tangent line would be a vertical line. You also cannot evaluate the limit if there is a sharp turn. Okay, so the one that pops out to me is absolute value of x. So he has a sharp turn at 0. So I can get you the derivative of the absolute value of x, but you can't evaluate it at 0 because there's a sharp turn. So you have to be continuous. You cannot be have a vertical tangent line, and you cannot have a sharp turn. Graphs of functions must be continuous and differentiable. Okay, all of these graphs fail to be continuous and or differentiable. So check them out. The first one's not continuous. It has a hole. The second one is not continuous. It has jump discontinuity. The third one is not continuous. It has a vertical asymptote. So there are your three types of discontinuity. So these functions are differentiable. They are not differentiable at C, at the point in question. But I can take the derivative of all of these functions. I just can't evaluate that derivative at C. It does not, the derivative does not exist at C. Okay, let's look at this one. It says the graph of f has a vertical tangent at C. So this thing has a vertical tangent line at C. Again, I can find his derivative. I just cannot differentiate him at point C. The next one is your absolute value. It has a sharp turn. And then there's this new one called a cusp. And it looks exactly like what you see. And we're going to see a couple functions that do that. You are not expected to know what functions do that. So don't worry that he's not in your kind of memory bank of functions. Just know that you cannot take a derivative at a cusp, at a sharp turn, at a vertical asymptote, or anywhere you are discontinuous. Okay, to sum it all up, we have the definition of a derivative. The derivative of the function of f with respect to x is the function f prime, whose value at x is, now you should know why we're using m, because we're talking about slope. M is f prime, which is this limit of y minus y over x minus x, provided that the limit exists. These are your notations for derivatives. These are the three big ones, but you need to be able to talk the talk. So the first one is f prime of x, the second one is y prime, and the third one, you don't say the over, you just say dy dx, which is the derivative of y with respect to x. For right now, don't worry about the bottom two. Okay, the limit definition of the derivative. And again, this is just kind of wrapping it all up. So graphically, the derivative of a function at point P is the slope of the tangent line to the graph at point P. Numerically, the derivative at a point is the limit of the slopes of the secant lines, or the limits of the difference quotient. The difference quotient is just that big limit formula that I said needs to be burned into your brain. Verbally, a function f is said to be differentiable at point a, f of a, if and only if it has a defined slope at x equals a. If a function does not have a tangent line at a specific point, then the function cannot have a slope there either. Okay, let's look at this. Given one point, We can find the instantaneous rate of change now. We can find IROC at x equals a. It is the slope of the tangent line at that particular point, which is the derivative. And then we've learned the definition of a derivative, and here they've just used a's instead of x's. If you're given 2 points, you can find the average rate of change, the AROC. You can find the slope of the secant line, or you can do slope just like we've done for 1,000 years, y minus y over x minus x. So given 2 points, you're talking AROC, slope of a secant line because it hits the graph twice, and then your regular slope formula. If you're given 1 point, you can now find the instantaneous rate of change at that point, which is the slope of the tangent line at that 1 point, which is the derivative at that 1 point, and this is the definition of a derivative. Verbally speaking, you are finding all of the following: the slope of the tangent line to f at x equals a, the instantaneous rate of change of f at x equals a, the derivative of f at x equals a, and the limit of the difference quotient of f at x equals a. And again, the difference quotient is just this thing. Remember, quotient means divide. So this is the difference quotient. Okay, that was a lot, but I cannot stress the importance of the foundation that we have just laid. So if it's not sitting well with you, I strongly recommend that you take an hour, ever long this video is, and just watch it again without having to write anything down. Just to make sure that you're hearing the lingo and the vocabulary, and also that you're really good with the algebra part of finding derivatives.